Chapter 4, Water Management. Objectives. 1. Describe how water influences plant growth and health. 2. Explain the principles of water uptake, transpiration, and the movement of water in the soil. 3. Identify soil characteristics and how they affect aeration, infiltration, and water holding capacity. 4. Discuss the factors that affect water loss from plants and how plants manage that loss. 5. Explain the importance of irrigation for urban landscapes and review the different methods of irrigation and advantages and disadvantages of each. 6. Discuss potential water problems related to salinity, toxins, and reclaimed water. 7. Discuss the advantages of mulching around trees and shrubs. 8. Explain why good drainage within the root zone of plants is important. Introduction. Water is vital to plants. Trees absorb water and minerals, dissolved in water, from the soil. A large tree can absorb hundreds of gallons, 1 gallon equals 3.78 liters, of water in a day, and as much as 95% of that water may be transpired into the air. Without sufficient soil moisture, a tree becomes dehydrated, stops growing, and overall plant health can decline. On the other hand, too much water in the root zone can cause tree decline as well. Maintaining adequate amounts of water in the root zone, neither too much nor too little, is critical for tree health and growth. Irrigation is a necessity in many urban planting sites, especially those with newly planted trees. Water can be applied in the amounts desired and at appropriate times with irrigation systems. However, irrigation must be managed wisely to avoid problems with quantity, rate, or water quality. Tree health can be adversely affected by either overwatering or underwatering. Good water management programs need to consider the water requirements for different tree species, soil conditions, irrigation systems and scheduling, water conservation practices, and drainage. Soil water. Various terms, many of which were introduced in the soils chapter, are used to describe both water retention and water loss. A brief recap is useful for this chapter. Water that drains through the soil is called gravitational water, while that which is retained is either capillary or hygroscopic water. Capillary water is held in the micropores of the soil and is generally available for plant uptake. Hygroscopic water forms a film on soil particles and is held too tightly by the soil for uptake by plants. Capillary water is also called available water, while hygroscopic water is unavailable water. For many soils, approximately 1/2 of the water held after drainage is available and the other half is unavailable. After gravitational water has drained, the soil is at field capacity, containing both available and unavailable water. When the available water in the soil decreases to a point at which a plant cannot take up enough to replace the water lost through transpiration, the plant will wilt. If soil water diminishes to the point at which a plant cannot recover even if more water is applied, it is said to be at permanent wilting point. Permanent wilting point is highly variable and depends on how an individual plant interacts with the current soil and atmospheric conditions. Water holding capacity is the total amount of water held by a soil after drainage occurs, when it is at field capacity. Water holding capacity varies with soil texture. Sand, silt, and clay content. Fine-textured soils, clays, have a greater water holding capacity than coarse-textured soils, sands. As a result, sandy soils will need to be irrigated for shorter periods, but more frequently than clay soils. Water moves downward, laterally, and sometimes upward in soils. Infiltration is the term used to describe water movement downward into the soil, while percolation describes water movement within the soil. In response to gravity, water moves downward faster and more extensively than it moves sideways. Both infiltration and percolation are affected by soil texture. Clay soils usually have much lower infiltration rates and percolation rates than sandy soils. Other factors that influence percolation and infiltration rates include soil structure and bulk density. Soils. Trees and water. The amount of water utilized by trees varies with species and size, soil conditions, air temperature, humidity, light levels, exposure, and wind movement over the leaves. Transpirational water loss from leaves is controlled by stomatal opening and closing and other anatomical adaptations in response to the environment. When transpirational water losses exceed the plant's ability to take up water from the soil, the plant wilts. An extended period of water deficit, drought, can cause root loss, leaf abscission, twig dieback, and plant death. Some plants develop extensive root systems to survive in arid regions, for example, honey mesquite, Prosopis glandulosa. Such plants develop deep, spreading roots that allow them to make use of soil moisture over a large volume and to tap into water sources found deeper underground. By accessing groundwater, trees and shrubs can survive extended periods of little or no rainfall. Other species have a different strategy for surviving periods of low soil moisture content. Some plants evade drought effects by shedding their with poor structure, such as compacted soils, will have lower infiltration and percolation rates than soils of similar texture, with good structure. In situations where the infiltration rate is low, water needs to be applied slowly and over extended periods of time. Leaves. Other plants become virtually dormant during extended dry periods, for example, California buckeye, Aesculus californica. In extreme examples of this adaptation, trees may go dormant and dry completely, springing to life with the return of seasonal rains, such as resurrection bush, Myrothamnus flabellifolius. Small leaves provide a reduced surface area from which water can escape through transpiration. A waxy outer layer, cuticle, may further limit moisture loss to the air. Tiny leaf hairs, pubescents, prevent water loss by trapping an insulating layer of moist air near the leaf's surface. Similarly, sunken stomata are protected by a small pocket of stagnant air that collects in the depression. Trees that developed some of these adaptations include olive, Olea europaea, and salsida, or tamarisk, Tamarix ramosissima. As mentioned earlier, species with relatively deep and extensive root systems have access to greater amounts of water than those with shallow root systems. Drought-tolerant plants are not only adapted to survive with minimal water, they can be adversely affected by supplemental irrigation water. Possible adverse effects include root disease and shallow root development. Shallow rooting limits the volume of soil a tree utilizes for water uptake, exposes the plant to fluctuating soil moisture conditions, and can increase the potential for uprooting in strong winds. Trees that are accustomed to fairly regular rainfall throughout the summer may begin to show stress after several weeks without rain. For some tree species, wilting is common during hot summer afternoons, but if the leaves are not turgid, fully hydrated again in the morning, the tree may be seriously stressed. Leaves may begin to turn brown or drop. If water is not added, smaller roots will begin to dry out and die, and the tree will decline. Trees growing where soil volume is limited, such as small parking lot islands or sidewalk tree pits and planters, often are the first to show water stress symptoms. Remember, if water loss from the foliage exceeds the rate at which it can be replaced via uptake by the root system, drought stress symptoms can develop. Trees growing in hot, dry, or windy locations can develop leaf scorch even if soil moisture is maintained at optimal levels. Also, anything that interferes with the vascular transport system can lead to drought-like symptoms. Girdling roots, lightning strike damage, trunk injury, or cankers. Vascular wilt disease, and similar disorders can all affect the uptake and transport of water throughout a tree's vascular system. Irrigation. Although irrigation requirements for trees are generally much less than those for other types of landscape plants, such as turf, irrigation may be necessary in some instances to maintain tree health. Requirements vary with species, tree size, and environmental conditions at the site, such as soil texture and structure, sun exposure, wind, and humidity. The need for irrigation can be reduced or even eliminated if proper planning and plant selection are able to match the site's environmental conditions with the tree's water requirements. Usually, trees in windy, hot areas, such as in parking lots and/or close to buildings, will require more water than those of the same species in shaded and/or wind-protected areas. Newly transplanted trees of any species require frequent irrigation, especially within the root ball. However, watering established plants at the same rate as new transplants can lead to problems. When the amount of water required to establish or maintain a given plant species in a given site is determined, irrigation schedules, for automated systems, need to address watering duration, frequency, days on off, cycle times, and distribution. As a general rule, frequent, shallow waterings encourage surface rooting, which makes the tree more vulnerable to desiccation, drying out, during periods of drought. Infrequent, deep soakings can encourage the development of a deeper root system and more drought-tolerant trees. Some soils, especially those high in clay, can be improved by being allowed to dry out between irrigations. The natural shrinking and swelling of the soil can improve the soil structure and water infiltration rate. Conversely, frequent, shallow irrigation may compact the soil surface and reduce the infiltration rate. Soils and mulch that are high in organic matter should not be allowed to dry completely because they can have a tendency to resist rewetting. It is often best to irrigate in the evening through early morning hours. This is particularly true for sprinkler irrigation systems, because less water is lost through evaporation and more water is able to infiltrate the soil. Also, many municipalities have instituted water use regulations that limit use to evenings and early morning hours. In situations where foliar diseases are a problem, it is important to avoid irrigation systems that keep moisture/humidity around the leaves for extended periods of time. Water should be distributed uniformly to as much of the root system as possible. If only part of the root system can be watered, such as when hardscape covers the soil surface, supplying water to accessible parts of the root system is better than not irrigating. In any case, efforts should be made to keep the root collar dry between irrigations. Maintaining wet soil in contact with the lower trunk, root collar, can lead to infection by soil-borne pathogens. Irrigation systems. Although various methods can be used to water trees, sprinkler or drip systems are most common. Both systems have advantages and disadvantages, however. Well-designed and maintained sprinkler systems can apply water effectively and efficiently. Appropriate valving, pipe sizing, head selection, and spacing are important considerations in system design. System monitoring, including head cleaning and repair, is needed to ensure continued effective operation. Although sprinkler systems can apply water uniformly across the root zone of a tree, they also can apply large quantities over short periods of time, leading to water runoff and erosion. Limiting application times to match infiltration rates and climatic conditions, and using low application spray heads, can minimize this problem. Drip irrigation systems apply water slowly to localized areas of the tree root zone, reducing the potential for runoff, erosion, and water loss by evaporation. Emitters, end-of-line or in-line, should be spread out over the entire root zone and kept away from tree trunks. To apply water to the expanding root system of young trees, emitters should be moved away from the trunk. Additional units may be required. It is important to recognize that emitters can become plugged and lines damaged. Sometimes, the only sign of a plugged emitter or broken line is a water-stressed plant. Frequent monitoring of drip systems is critical. Other methods to irrigate trees include high-pressure water injection, soaker hoses, basin irrigation, and temporary, portable drip systems. Portable drip or soaker systems can serve as an effective means of supplying water to newly planted trees, to transplanted trees, and to established trees during periods of drought. Basin irrigation distributes water uniformly to the limited root zone of newly planted trees. High-pressure water injection can deliver water deep to the root zone but may bypass absorbing roots at the soil surface. Soaker hoses are portable and can apply water slowly where runoff may be of concern. Many irrigation systems are designed and installed primarily to irrigate turf and other landscape plantings. Too often, trees are not properly considered in irrigation management programs. Excessive irrigation of trees is becoming a problem in many urban and suburban areas. Fungal problems such as root and/or collar rot are often associated with excessive irrigation. These conditions are particularly troublesome in instances where irrigation is applied directly on the trunks of trees. Tree species that are adapted to dry summers and native to such climates are prone to problems associated with frequent irrigation. Often, tree root systems are damaged during the installation of below-ground irrigation systems. Roots can be easily cut when trenchers are used. Damage to roots can be minimized by proper system design and by using pneumatic air tools, rather than mechanical trenchers, to dig irrigation trenches. Water conservation. Water is a very limited resource in many areas, and water conservation needs to be considered as an integral part of water management programs. Minimum irrigation provides only that amount of water needed to maintain tree health, growth, and appearance, canopy density and leaf color, using efficient application methods. Xeriscaping, or drought-tolerant landscaping, has become a popular design alternative for property owners living in areas that lack seasonal rainfall or readily available sources of fresh water. Although traditionally practiced in dry regions, the principles of xeriscaping may be applied in a wide range of environments, as a means of reducing landscape maintenance, water use, and irrigation expenses. The term xeriscape, originally trademarked by the Denver Water Department in Denver, Colorado, has become a commonly accepted term within the green industry. However, confusion with the word xeriscaping has caused the term xeriscaping to lose favor. When planning a new landscape where minimum irrigation is to be used, plants with similar water requirements should be grouped together and irrigated on the same schedule, hydrozone. This technique usually employs the use of highly efficient irrigation methods and plants with low water requirements. Keep in mind that new plantings require more frequent watering until they develop established root systems. Also, caution is in order when transitioning to minimum irrigation because plants must adapt to lower soil moisture conditions. Minimum irrigation practices require an understanding of water budgets, plant and soil water loss, evapotranspiration, or ET, water holding capacity, application rate, infiltration rate, and irrigation system efficiency. Reference evapotranspiration, AT, is measured in many locations and is used to estimate water loss from agricultural crops and tough grasses. This information has been adapted for trees and other landscape plants. In many locations, tables or charts of average ET are available through cooperative extension or agricultural department offices. Another approach to minimum irrigation employs soil moisture monitoring. Devices such as soil probes, tensiometers, and electronic moisture sensors are used to measure soil wetness or dryness. Carefully tracking soil moisture before and after irrigations allows the amount of available water to be assessed in order to adjust irrigation recommendations. Arborists may be called on for advice when irrigation systems are being designed, installed, or adjusted. An understanding of the water requirements of trees and other plants in the landscape is an essential part of estimating how much water will be needed and at what frequency. Information regarding ET, water holding capacity, irrigation efficiency, infiltration, and application rates needs to be put together so that an appropriate watering schedule can be developed. Recycled water. The water source for irrigation affects the quality of the water. As water flows over or through soil and rock, mineral salts dissolve and are carried up by the water. Excess salts in the water can be detrimental or even toxic to plants. Recycled water can be high in salts as well as other chemicals. These chemicals can raise the soil pH, increase soil salinity, cause problems with phytotoxicity, and clog irrigation nozzles. Recycled water can also be high in essential elements such as nitrogen, phosphorus, and sulfur. Irrigation water taken from landscape retention ponds can have high levels of sodium and chloride salts. This is especially true where parking lot runoff is captured. If this water is sprayed on foliage, severe leaf scorch can result. The pattern of scorch on the tree canopy will coincide with the R of the irrigation spray pattern. Successfully using recycled water depends mostly on the soil type, water quality, and sensitivity of the plants to salts. Because good drainage is essential, sandy soils are more suitable for irrigation with recycled water. More frequent irrigation is usually necessary, however, because drought stress will occur at higher soil moisture content under saline conditions. It is important to monitor plant health and soil conditions frequently when irrigating with recycled water. Efforts to select salt-tolerant plants can reduce the impact of saline water sources on the overall health of the landscape. With sprinkler irrigation, less frequent irrigations of longer duration will lessen the likelihood of salt buildup. If irrigation water does not penetrate the soil deeply, most of the salt brought in by that water will remain near the surface. Under saline conditions, irrigation may need to be provided more frequently. Soil damage can result from excessive sodium in irrigation water. Mulch. Water conservation techniques also include the application of mulch around trees and other landscape plants. Mulching can improve soil structure and infiltration, reduce soil moisture evaporation, moderate soil temperature, limit weed competition, which further reduces evapotranspiration and soil water loss, and reduce soil compaction and erosion. Organic mulches have the added benefit of increasing soil organic matter as they decompose, which enhances soil biology, fertility, and structure. Aside from improving soil and moisture conditions, mulch can also provide a landscape with a well-kept appearance and can reduce trimmer and lawn mower damage to trees. Some commonly used organic mulches include bark chips, pine needles, and nut shells. Other water conservation methods. In addition to mulching, various amendments are sometimes added to soils in an attempt to increase water holding capacity or improve drainage. Because amendments vary in their capacity to improve soil conditions, it is important to select an amendment that will achieve the desired objective. Incorporating organic matter into soil may be beneficial, but the effects are often short-lived because the organic matter decomposes. Soil additives that attempt to increase water holding capacity are currently being researched, but none have gained widespread use in arboricultural practice. Landscape water usage can be greatly reduced by limiting the amount of turf areas on a property. Mowed tough grasses have shallow root systems and quickly lose their ability to access plant-available water as it drains deeper into the soil. As mentioned earlier, proper plant selection can greatly reduce irrigation demands. Fertilization of turf, trees, and other plants should be avoided during dry periods. Many fertilizers, especially quick-release formulations that are composed of inorganic ions, salts, may cause fertilizer burn in plants. Additionally, the flush of growth associated with fertilization may further stress a plant if sufficient water is unavailable. Antitranspirants are chemicals sprayed on plants to reduce water loss through transpiration. These chemicals work either by forming a thin, impermeable coating on the foliage or by triggering stomatal closure. Antitranspirants are sometimes applied to transplanted trees that will be transported long distances. Caution should be practiced when using antitranspirants. Studies have shown them to be phytotoxic to some species. Transpiration also serves as a means of dissipating heat. Preventing transpiration limits a plant's ability to cool itself. Research has shown that, although antitransparents may initially prevent warm season transplant mortality by reducing moisture stress, long-term survival can be diminished as internal plant temperatures reach lethal levels. In addition to preventing stomatal water loss, antitransparents reduce carbon dioxide intake. Limiting carbon dioxide reduces the rate at which plants can actively photosynthesize and may increase the amount of time needed for establishment in the landscape. Additionally, reduced photosynthesis may limit a plant's ability to cope with stress and reduce overall plant health. Antitransparents should not be used to compensate for poor cultural practices. Selecting plants that are capable of adapting to the site conditions is vital to ensuring their survival, while reducing overall water and maintenance demands. Flooding. When soil moisture content is above field capacity, water moves downward through macropores in response to gravity infiltration. This movement can be relatively fast or slow, depending on the soil's physical characteristics, texture, structure, bulk density, depth, and layers. Soils with relatively slow rates of water movement are referred to as being poorly drained. In poorly drained soils, water can occupy macropore space for extended periods, restricting air movement. Flooding can be very damaging to trees. The lack of oxygen, anaerobic conditions, in the soil suffocates roots, changes the chemical composition of essential elements, can lead to fermentation in root cells and buildup of toxic compounds, and can create mineral toxicities. Lack of oxygen can also harm the living components of the soil ecosystem. The longer excess water remains, the more tree health deteriorates. For some species, just a few hours under flooded conditions will cause photosynthesis to stop and transpiration to decline. After several days, some root loss is experienced in most species. If conditions persist, some species will decline and die. Tree species adapted to floodplains can tolerate longer periods of flooding compared with upland forest species. For species that survive flooding, there can still be long-term consequences. Some will be predisposed to stress factors, including drought and secondary pests, such as root discase, cankers, and borers, for which they may not be able to generate an adequate defense. Trees that have experienced flood conditions are prone to toppling due to soil failure and/or root loss, and they may also have a higher incidence of root or collar rot. Additionally, grade changes due to erosion and soil deposition can lead to long-term stress. Trees that survive flood conditions should be inspected for hazards and structural integrity of the root system. Changes in grade should be corrected if possible, and measures to improve soil aeration should be considered. Drainage. Preventing drainage problems is a key strategy for limiting injury to trees. It is important to consider the grade and drainage flow pattern during construction or landscape development. Attempts should be made to avoid the creation of low spots where water could accumulate or drain slowly. If the site is not already developed, adjusting the grade is the first choice to avoid drainage problems. If a developed site is known to have poor drain age, drain tiles can be installed prior to planting to prevent drainage-related problems. Drain tiles are made of clay, concrete, or plastic, although plastic is most commonly used for landscape purposes. The depth and spacing of the tiles depend on soil and planting conditions. Drain tiles remove only gravitational water from the soil. Heavy clay soils or improper irrigation practices can still create situations where the soil remains too wet, even after the gravitational water has drained. Drain lines should be placed above any deep, impervious layer or hardpan and should slope away from the plantings at the rate of 1/4 inch per linear foot, 2 centimeters per m. Tiles are normally placed on sand or fine gravel about 3 feet, 1 meter, below the soil surface. The holes in the drainage tiles should be placed facing down so that water enters the drain from below, after most of the large particles have settled out. Wrapping drain tiles in geotextile fabric can help prevent soil penetration and clogging. Drainage problems in urban landscape sites are often not recognized until after planting is complete. If drain tiles cannot be installed, surface drainage may be improved by changing the grade or trench and/or surface and subsurface flow may be managed to prevent impounding and erosion. However, care must be taken to avoid damaging the root systems of existing trees. Soils can also be amended to improve drainage, typically with organic materials. With the selection of appropriate materials, macropore space can be increased. However, drainage improvement may require the addition of a substantial amount of amendment and needs to be done prior to landscape development. In soils where water infiltration is slow, steps can be taken to avoid standing water. Irrigation should not be applied faster than water can infiltrate. Slow water application can help prevent puddling and runoff. If the problem is caused by compaction, soil aeration may also be considered. Even with proper care, there are limitations to the effectiveness of maintenance practices in controlling drainage. Careful plant selection is important in choosing trees that will adapt to the soil's drainage conditions. In highly developed areas, the large concentration of impervious surfaces interfere and can greatly reduce water infiltration into the soil. As a result, stormwater runoff is a major concern in many urban areas. To keep streets and sidewalks clear, runoff is often channeled through a series of gutters, canals, and storm drains, and is then directed to a nearby body of water or processed in a wastewater treatment facility. As water flows over streets, parking lots, and other hardscape elements, it carries pollutants with it, such as motor oil and de-icing salts. If left untreated, this water can severely degrade the water quality of nearby lakes and rivers. However, treating storm water before it enters a local watershed is costly, and large rain events may overload water treatment facilities. As a result, reducing overland water flow and increasing water infiltration into the soil is both environmentally and economically beneficial. A rain garden is a landscape feature specifically designed to collect and hold stormwater runoff. Rain gardens are often incorporated in a landscape to capture water from parking lots, downspouts, or sloping lawns. Although the plants incorporated in a rain garden must be tolerant of periodic flooding, a rain garden will not always be filled with water. Plants in a rain garden should also be tolerant of dry periods, or supplemental irrigation will likely be necessary. Both native and non-native perennials, shrubs, and trees are often incorporated in rain garden designs.